Hello! Welcome to the penultimate session of B461 for spring 2021. That's right, we're almost over. And to that end, I've sent out an announcement that noted that I am pretty much caught up with what I expect to be caught up with right now. Uh, there are some people that have told me, hey, here's work in the past that I haven't gotten to yet. I know that, but everything else should be good to go. So, if you have a bunch of dashes, or I don't really know what it looks like in the student view, I guess, but if you have a bunch of grades that aren't in the grade book and you haven't talked to me about it already, I'll still take it for a discount on your points. But keep in mind, whatever Canvas says your grade is, if you have a bunch of missing work, it ain't that. That's way higher than it'll be with zeros in those spaces. So you have until the end of the week to make sure that everything you want to turn in is turned in. Otherwise, hey, we're almost done, right? So let's get almost done here. So let me let's go to a web browser and make sure that we have the very end of the course calendar correct. So today we're talking about transactions. Next time we'll talk about database optimizations, how queries get optimized. That's what I just about said there. And the only thing you have out right now to do is homework 8. The final, is that correct? My calendar isn't open yet. The final will be during the finals week. Do a little bit earlier than finals week ends so that I have time to grade everything and get finished. It'll be just like the other tests. Yeah, that is correct. So Wednesday, sometime between Wednesday and it looks like Sunday, I'll have you do that test. And it'll be like the other tests where it's a Canvas quiz and you just fill out the quiz as a test. All right. So without further ado, let's talk about transactions so that we can get this show done. So transactions is chapter 20 in your book, and it's all about how to make sure that when we do operations in a database, that we do all of the operations we expect to do, which could be more than one operation, without interruption, right? So what we want is we want to make sure that we can do multiple operations but not be interrupted. That is, we know that the integrity of the database is good because we were just doing several operations that modify the database and nothing will have updated from underneath of us, right? And more than that, how do we know that only our particular operation is the one happening on the particular data that we're looking at, right? And so transactions are the way that we make units of multiple transactions and make. Oh, I misspoke that. Transactions are how we make units of multiple queries run independently and safely, right? So we're going to look at some things with transactions and like what affects a transaction, what really drives a transaction. We'll talk about the ACID transaction guarantee, which is the normal guarantee that you have for transactions in most databases. And I've got a small example of a database and some operations that you might want to do to that database to perform a transaction. All right? So we start with what the heck are these transactions? And essentially all these are executions of programs where we're going to guarantee that a sequence of reads and writes is unique for that user, right? The database doesn't know what a user is doing. So a user is going to write a program, and it's probably going to do a whole lot of work. Some of that work is going to happen offline on the client program, and some of that work is going to happen online with the queries that that program sends to the database. And there's all kinds of stuff that could be happening while those processes are waiting to operate, right? We could be waiting for I/O, we could be waiting for network traffic. Somebody else can send queries to the database in the meantime. And our database needs to be able to kind of give priority to the user that is operating on particular data, right? And that's what our transaction does. So when we have a transaction, what we're talking about is a collection of operations that represent some operation in the real world that's happening, right? So in our parlance as the client of the data, we either want all of our operations to happen as one unit or they don't happen at all. And that makes it atomic in that it's one operation, it's one operation made up of many smaller operations, potentially. And so, for example, if you're going to transfer money between accounts, you want to make sure that when we deduct money from one cell of a table, we add that money to the other cell, and that either works or it doesn't. And B, that if I deduct money from one, I can't deduct money from the other before adding, right? We want all of that to happen as one unit, right? Same thing if I'm going to purchase a bunch of products. I was just making a purchase this morning that was actually a pretty good example of a transactional issue. So there's a tools outlet called Direct Tools that sells like bottom barrel pricing on home improvement tools. I needed a power washer. The side of my house, right behind me actually, fills with mold, and I really need to clean that off. Well, they had a sale today. And so I was able to buy a very nice power washer, an electric power washer, but like one of the nicer end of the electric power washers for about half price. Now, if something is being offered at half price, it is bound to become a popular offer. And one thing that they need to make sure of is that as customers purchase items, they can't purchase more items than are available in stock. So I was having credit card problems, as you do. They were denying my card, and CV codes were wrong and all that kind of stuff. And so I was sitting there kind of panicking, actually, because I was like, I really need this pressure washer. And I need this transaction to go through so it gets to me, right? And so the transactional issue here is that I want to know, and I don't know this about this company, just to be fair, but if I were this company, this is what I would be doing. I would want to know that if a user has something in their cart and they have successfully purchased that item, that is, they have hit the pay button and it went through, I want to make sure that I don't sell somebody else the last item that they just purchased, right? That's a transactional issue. We want to lock the database, or we want to lock that table or those rows, depending on what it is, so that you cannot purchase more items than exist by making purchases in parallel, right? So when we write transactions, usually what's happening is we are writing an application that is using the database, right? Usually what you do professionally with a database is not operate the SQL Management Studio or Data Grip or something like that. It's usually you're writing a program that executes SQL statements or executes store procedures potentially to guarantee that you have client code separated from database code and separated from database concerns. And when we pass these SQL statements to the server, what we want to do is tell the server, I want to start a transaction, I'm going to do some operations, and when I end that transaction, then that's that atomic unit ready to send and ready to go, right? So the reason we write these programs, well, generally speaking, individual SQL statements are not enough to do operations that we're interested in, right? Usually, if we have to do anything very interesting to the database, we're going to maybe update multiple tables or insert to multiple tables. And each one of those SQL statements that we write to insert to each table has to be separate, right? You don't insert into table 1, comma, table 2. No, you insert into one table at a time. So for example, we have two clients, A and B, and each one of these is its own atomic transaction. They happen separately, right? So in program A, we get item X, we subtract something from it, and we write it. We're going to get item Y, we're going to subtract to Y and write it, right? And in program 2, we get X, we add something to it, and we write it, right? So we have two queries that operate on the same data, X. And it happens that T1 does a little bit more than T2, right? This is giving us opportunities for a race condition. Anytime something can happen in parallel, and this can absolutely happen in parallel because we don't know that A and B are the same computer sending requests to the database or anything of that nature. So we're looking at these as two events in time that could happen one before the other before the one, or side by each. So what can happen here? Well, one problem that could happen is a lost update. So look at this timing. So as time goes downwards, so we start up here, transaction 1 gets X and subtracts N from it. And in the meantime, number 2 here gets X and adds M to it. But in between adding M and writing X back out for T2, T1 has written its copy of X and moved on to Y. But T2 then writes X, which means that we've lost T1's X value because we just overwrote it with whatever we believe X is in T2. So we want to prevent this kind of a race from happening because this is bad. We want to make sure that all of the things that have to do with X happen in an atomic unit, in a transaction, so that we can control and make sure that we don't lose data, right? So ideally, we would have a situation where the entirety of T1 happens before or after T2. So in this case, T1 fails and has to change X back. And the reason for that is T2 has updated in the meanwhile, right? And we want to make sure that that is not happening, right? So another example here, we have an incorrect summary. We have a situation where T3 is running and it's supposed to add all these items together. Part of its adding is X and Y here. If we let T1 and T3 run side by each, well, T1's going to change values in the meantime of T3 trying to sum values, right? We can't have that. Right? These are all bad situations where values are changing while somebody else is doing operations and trying to work on the same data at the same time. This is the same problem you run into with Git. Like if two people are working on the same file at the same time, you get a conflict and you have to resolve that conflict. In this case, we want the database to resolve conflicts automatically. And generally time is the way that we're going to resolve those things. Who gets there first and who gets there last. So all of this leaves out some other things that can happen. Like we might be changing multiple tables, we might be doing loops, we could have external resources operating on the database, and we want to make sure all of those things happen atomically. We want to make sure all of those things happen reliably, because we're the database, we're the source of truth for all kinds of applications. We need to make sure that our data is correct. That is thing number one for a data. Make sure your database rather. Make sure your data is correct. Make sure that it is reliable. So if we're running a transaction, what we do is we say begin and end transaction, and we have a commit. And that commit is the moment that we say, now I'm giving up control, my transaction is finished, everything worked great. You can now give control over to another SQL statement. So this is the concurrency control that we have in a database, is starting a transaction, doing a bunch of things, and committing that transaction, right? On the other hand, there is an opposite to commit, and that is rollback, right? So if we run the rollback keyword, that means something went wrong, we're going to abort this transaction, we're going to give up, and everything that we've done in the transaction will get undone by the database. So as you run a transaction, as you run something that we say this is one set of commands, the database is actually just keeping a change log of what's happening in the database from your commands. And on commit, it's going to apply that change log. And on rollback, it's just going to throw the change log away, right? So on rollback, we return to our previous state. We don't do anything, right? So why do we roll back? Well, it could be a logical problem, but it could also be somebody said, hey, this isn't what I want to do. Or it could be a crash. So rollbacks are automatically on timeouts. And so logic errors, system errors, all of those sorts of things can initiate rollbacks. And this is the safe way to program for a database, to explicitly start transactions, explicitly commit, and explicitly roll back when you encounter an exception. So the guarantees that we have, standard databases give you an ACID guarantee. And ACID stands for atomicity. I'm going to pronounce it that way. Consistency, isolation, and durability. If you go looking for a database and it says it's a transactional database, and I don't care if it's a SQL database or not, ACID is the guarantee that you generally look for so that you know it supports transactions correctly, right? So atomic transactions. These are transactions that only have two result states. They happen all at once. They either commit and the changes happen, or they abort or roll back and no changes happen. There's no in between, right? So if you run 20 SQL commands, if you run 20 insert statements in a transaction, atomicity gives you the guarantee that all 20 of those commands actually ran. We didn't just run 10 of them, we ran 20 of them, or we ran 0 of them, right? So there's no halfways with atomic transactions. So that's a very important guarantee, because we want to make sure that we don't have to like rebuild history when we've run what we would consider to be standard commands, right? So when we were running transactions, there's no halfway again. If any part of our transaction fails, or if any part of our transaction says, oh, abort, the entire transaction aborts and nothing happens. But if we do get to a commit, all data gets written, not half the data. So the database is guaranteeing that promise. Integrity is not one of the ACID definitions, but it is important. Just to recall that when we're looking at a database, not everything is going to be valid at all times. There are going to be violations to constraints that happen. And the integrity of the database must always be kept up, right? So, for example, keys have to be unique. You might have rules set in the database that certain values have to be of a certain domain and range. Foreign keys have to exist in other tables and things like that. So integrity is this guarantee that we want all the time in our database. Is not part of ACID, but ACID is part of guaranteeing integrity, right? Because if I'm inserting data, I may have to turn off foreign key constraint checking in order to successfully insert data and then turn it back on when I'm done and verify that everything I did was correct. So a lot of these kinds of constraints are very explicit. Some of these constraints may not actually exist inside the database, but we want to guarantee that our database always has integrity when we've finished operations. Because again, if we don't have a database that is available and correct, then we have nothing. Like we cannot depend on an application that has a faulty database. It's going to have the wrong data in it. And that could be a business concern, that could be a safety concern, but we have to worry about these kinds of things. So, sidebar done there. The next ACID guarantee is consistency, right? And consistency says that we make sure that our transactions take us from one valid database state to the next. That is, we keep integrity, right? That's why we mentioned integrity. So during a transaction, we may have a situation where constraints are not met, right? We might have to violate constraints to make a set of commands actually finish. But at the end of the transaction, transaction has to be consistent, and we must make sure that the database is in a valid state. If we don't, that's why we roll back, right? If we notice that, hey, I did all the things I was supposed to do and the database isn't in a valid state, we roll back, we abort, we don't do it, because we always want our database to be valid. And consistency is one of the ACID guarantees. So even though we have the ability to turn consistency checks off, our database will check consistency when we try to commit. And if a commit fails, we roll back. So like when it tries to write data to the database, may fail. We have to handle that. And the programmer is responsible for consistency as well. So if you have business logic rules in your client application, you have to make sure that those rules are met. If you have a NoSQL database, you doubly have to make sure that those rules are met because they don't guarantee anything about the schema of the database. The I in ACID stands for isolation, right? And this is that any concurrent execution of a transaction, right? We want to make sure that if there are two transactions running in parallel, the difference between them running in parallel and sequentially is nothing. Which is to say that if two transactions run in parallel and they touch the same data, they cannot run in parallel anymore. We want to make sure that we can lock data that's going to be modified or read by two things simultaneously. And there are different levels of isolation, right? So there's repeatable reads where we say, hey, transactions can only see data that's committed. We can change that and say that transactions have write locks. And we can lower it all the way so that transactions can see all data and they don't have this guarantee. This is often tunable in databases, but the important thing here is that as you have more isolation, that means you're locking your database more and you're slowing down parallel execution. Okay. So in this isolation world, like what happens in this situation? I have two transactions running And the first transaction selects out of users. Second transaction inserts into users. And the third action in transaction 1 has another select. Now, if I run these two transactions in parallel, they're doing operations to the same data set, right? Bob that I'm inserting here is 27. He should show up in both of these queries. So if I do something to get a list of users, I am going to do some operation on those users, and I check those users at the end. If these two transactions weren't isolated, I run into a phantom read. If they are isolated, that is to say that, well, I'm inserting here so I cannot do these operations at the same time, we will serialize the two operations to make either transaction 1 happen first or transaction 2 happen first. Then internally, transaction 1 becomes consistent and isolated. That's the serialized. If I have a read lock, we could only see committed data, so transaction 1 would see the data as though transaction 2 hadn't run yet. Because transaction 1 started, it's only going to see committed data as of when it started. And these guarantees, again, mean that transaction 1 is in itself consistent and therefore not going to just go haywire as data is changed out from underneath of it. Remember that you can do anything you want in these transactions. So, like, transaction 1 could be trying to insert Bob, and we could end up with double Bobs. It would be especially bad if they had the same ID, and then we don't have database consistency anymore. So we want to make sure that these things can't happen. And when we're doing these concurrent transactions, well, remember that we think about our local query. We're thinking about, like, how do I do this operation on users? How do I insert Bob? But really, it's a global thing that's happening, right? Because there are going to be many operations happening at the same time, and every program may run its own queries and have nothing to do with each other. So our database has to ensure that we don't have these interactions. If our database doesn't ensure that our concurrent actions happen in isolation, then we're going to end up with corrupted information, right? So the last point in ACID is durability. And that means that once we have made a commit, it is permanent. It gets put onto the disk, and we are not going to return from the commit until we know that data is there forever, right? So durability is a really important term, especially in, like, distributed databases where you could have data spread across multiple servers. We want to make sure that we don't have information in memory that we've said is committed, because if we do, we could have a power outage and lose that information, and suddenly a guarantee that we gave the user is not the case anymore. This uses a thing called the two-phase commit protocol. And the two-phase commit protocol, I'm going to go load that page up real quick. Two-phase commit protocol. What the two-phase commit protocol says is that there are two stages to getting data written and confirmed. We request a commit, and we make sure that every party that is involved in writing that data says, I am ready to write this data. And then we send the commit phase, which says that every receiving party has said, yes, we're ready. And therefore the coordinator says, go ahead and do it. If any party that is responsible for writing data says no, then we roll back, right? We don't do it, we abort. The two-phase commit protocol means that we have a coordinator, the query runner, who says, I'm ready to commit. and says, oh, hey, we're ready, please vote, participants are going to be all of the things that are writing to disk. That could be one server, that could be 10 servers, that could be 10 servers in a REST protocol, doesn't matter. Everybody has to say yes or no. So the coordinator can say, okay, go, or somebody said no, forget it, right? Once they send that commit message or rollback message to all the participants do the commit and acknowledge that they have. Once the coordinator gets all of those acknowledgements back, it will tell the client, hey, we successfully committed. And that's what happens when you run a commit on the database. So this is the normal way we get durability in databases, is something like the two-phase commit protocol. Now there are actually there's a three-phase commit protocol, but either way, these are methods for distributed systems to guarantee that what we say we've done, we have actually done. So I do have an example. And so in our example, we've got an information system that is an ordering system for like a business, right? So we have a few tables. We have a stock table that tells us what products we have in what stores and how many. We have a product table that tells us what products are. And we have an order table that says, hey, I want to get a product and ship it to somebody, right? Now, importantly, in our system, we're never going to delete rows. We only change things like quantity. So in store, when we purchase something, when we create an order, we'll insert into the order table and we'll decrease the quantity in store by the quantity that we ordered. When we order, we have a received to say that the order was received. We don't remove the order after we're done with it. We just say, hey, it's done. Here's the time it got received, right? So until the goods are received is null. And we'll have other tables, but importantly, these are the tables we care about. So, example constraints, right? In store, we've got the key, that is the product ID, and the store ID is a composite key for in store. In product ID is the primary key, and in order ID is the primary key. And as for foreign keys, well, in-store.product ID must be a valid product.product ID, right? And likely there are going to be a bunch of other foreign keys that have to do with tables that aren't here. So we probably have a store table to relate store ID to, et cetera, et cetera, et cetera, right? There's a product ID in order too that must reference product. So, constraints on the data. These are application constraints, data constraints, things that the programmer has to make sure are correct. We can't ever have negative items in a store. That doesn't make sense in the real world, and it doesn't make sense in our model, right? We can't receive an order, right, in the future, because received indicates that it has happened and it is finished. So it always has to be less than the current state. You cannot receive an order in the future. We have some business rules outside of our data rules, right? And in our business rules here, we're saying that for all of the products that exist, for all stores and warehouses, we have to have at least 50 items, which is just a business rule that says if there's less than 50 items, we got to get more, right? We want to have 50 items ready to go at all times, right? And the second one here, the sum of all quantities among all stores, warehouses, I think that's supposed to say less than 70. We don't want excess stock. I'm pretty sure that's an error. If that's not the case, then we have to have an order outstanding, something in the order table that says, hey, something's wrong with those tables, but only because something's in flight. So the transactions that we want to make to this, well, what operations would we need to do? we would need to be able to make a sale, which is to say subtract from our stock and create an order entry. We'd need to be able to accept a return, which is to say negate an order and put it back into stock at a store. Right? When we receive an order, we need to record it. We have a restock, which puts stock back in our stores, a clear out, and a transfer, right? So when we write these transactions like make sale or clear out, in this case, we need to write SQL that makes this thing happen. And so this is 3 commands, you notice, right? We start a transaction. We're going to select into this temporary table, and this is a trick that I haven't told you, but when you, depending on your SQL dialect, when you have a colon before a table name, that is a temporary table. So what we're doing here is we're saying we have a store and product that we want to clear out. And so for that product, we're going to put things back in the warehouse for the product, and we're going to empty the store for that product. Now, all of these things have to happen atomically. So when we've done all of those things, we'll commit the transaction and we're done. So this transaction moves the stock from the store to the warehouse safely and happens as one unit of operation. Another example, restock. This means that our store has less than the amount that it's supposed to have, which I think was 50, right? And we need to bump it back up, right? So we can start a transaction. We're going to add whatever quantity is back, subtract the quantity from the warehouse. We're going to check the store, and if it's not in the store already, we'll insert that quantity into the store. Otherwise, we'll add the quantity to what the store already has. So if the store didn't already have this product, we need to add to it. If it did, then we just need to update its quantity. And again, at the end, we commit, and we've finished our transaction. We've done all these as one step, so if somebody else were trying to change the quantity of this product, say there was another store restocking at the same time, then we won't let those things happen at the same time because we want to make sure that this number stays correct. Otherwise, we have a problem. So, what are we doing here? We're trying to keep integrity, right? When we want to do an operation, we have to make sure that all of our data is okay. So like, for example, if we make a sale, we need to reduce the in-store quantity because we're selling that quantity. We need to check how much we have. And if we don't have enough, then the sale fails, we'll roll back, right? If 70 is like if we have too many in transit, we may have to roll back. If we don't find any of the product, we need to order some for whatever that value is. We need to stock it, right? All of these things give us the ability to check those business logic rules and the data logic rules and make sure that we don't run a command that is invalid. We maintain that integrity. So we note that we don't need extra logic for the business rules in some of these things. And why is that? Well, in those rules, we go back toward them, they aren't modifying what goes out to the user, right? Restock and clear out and transfer, those aren't changing the amount of product that we possess. They're just changing where that product is. So we need no extra logic for those like we do for order things, where we have orders that are in transit to the user. That means we've lost some objects. And we have to worry about those 50 and 70 numbers, right? So our database's integrity, as I mentioned, is kind of paramount. And there are threats to that integrity. If we have an application run a rollback, we need to make sure that the rollback happens successfully. If we have a system crash, we need to make sure that when the system comes back, a transaction that was halfway through is rolled back, not committed, or doesn't ever happen at all, right? And we need to make sure that concurrent activity is guaranteed to happen in isolation and doesn't affect each other concurrent activity happening, right? So when we have an application rollback, right, we want to make sure that if we notice that integrity is false and we have a rollback, the system reverts to the earlier state and that the transaction had no effect, right? Now, how do we do that? We generally just don't commit to the disk until a commit happens. We write to what's called there are different names for it, but transaction log or something of that nature. It's a memory area. And that way, if we need to not commit something, we just don't do it, right? So for example, if we're making a sale and we reduce the quantity and the new sum is below the 50 that we said that we have to have no matter what, we abort the transaction. The system has to restore the previous value of quantity, and it has to know what that value was to do that. How's it going to do that? Well, again, it's really a changelog system, right? And so what we're saying is we have an area of the disk that is the table that exists for real, and then we have some kind of a queue that has the changes that we're making for various transactions. And as these transactions get committed to the table, they can get popped off. If one fails, then it just gets popped off and we don't commit it to the actual table. So this is just like Git in that it's a change log. It's not actually what's necessarily on the disk. And we can apply and revert that change log as we see fit. It's a difference between the data before and after the transaction. So in databases, always look for the ACID support. You want ACID. And most databases support it. It's actually kind of weird for them not to, especially most SQL databases. This is a fundamental feature of databases. And if you go looking at a comparison, so let me pull that page up, I think. Go. Browser. If you look at a comparison of relational database management systems, you can start learning about all the options that there are out there, and there are a lot. And so here we have kind of release information. So we have like how old the database is and how stable it is and what its license is. But as we go down, we might find operating system support, which is of course important. Fundamental features here. Look at this. ACID, referential integrity, transactions, fine-grained locking, Unicode support, type inference, interface, right? If I sort this table by ACID, we can see all of the things that support ACID transactions. And you're probably going to find most databases you're interested in here in the green. Notice SQLite supports this. That's good. MySQL supports this. What I notice about this is every single one of these, except for whatever the hell Superbase is, have a green light there. Right? So this is something that you can pretty much consider standard. Now, these are all relational databases, not no SQL databases, right? So if we find a no SQL comparison, which is going to be in a very different place, they might have a C also for it. Comparison of object relational, comparison of database tools. Maybe we won't find exactly what we're looking for, but you can probably find a good comparison of, actually here, key value, column oriented, document oriented, no SQL. That might have what we're looking for. Some of these NoSQL databases do support ACID. So here you go. Here's the ACID and join support table. So all of these say ACID. That's good. These are databases that you can trust that they will at least write your database and keep its integrity up. But there are many more databases that are in that than are in that ACID list right there. Right. So going and comparing databases when you want to consider a database is a very important step. And so you want to look for that kind of thing. So in summary, transactions are important. They give us safety in what is a distributed system. Databases are a situation where somebody else has made distributed computing easier for you. And the way that they've made that easier for you is they've given you the tool of transactions. We have a standard in ACID that gives us a guarantee about those transactions. We must use those transactions to guarantee our database is atomic. Single query operations often automatically have a transaction, but if you're writing multiple queries and expecting that the results have to do with one another, you need to use transactions to do so. Let me show you. You think about this for a second. I'll show you. I think I showed you this before, actually. But here's the database library I use for SQLite. And, well, it's really for any SQL in Go. And they have some examples here where they have usage. And every example that they run, notice this, we have database.must execute schema. So it must execute this command that creates the schema. But then we start transactions. We begin transactions. We exec statements in those transactions, and we commit those transactions. Always, when we're trying to do something that is related to other queries, we want to do something like this, and it's going to look like this in whatever language you're using. I don't care if it's Go or C# or what. Single queries, it doesn't matter so much because it's a single query, it's already atomic. But for anything where you're going to do multiple actions, you need something that looks like this, where we start and commit a transaction to execute code. So you want to use explicit transactions. All right, so that's it for transactions. We'll have optimizations on Wednesday, and that'll be our last topic. All right. I'll talk probably next Monday about what I'm doing on the final. So I'll have maybe a really, really, really short stream on Monday. Maybe I'll talk about it next time, but I think it'll probably be Monday that I do that for. All right. As noted at the beginning of class, make sure that if you have anything outstanding that you let me know if you haven't already. And I hope that you have a great end last week. All right. See you guys.